All right, so our next set of reactions are called the Claisen condensations. To be honest, it drives me nuts that they're called Claisen condensations instead of Claisen additions, because they're very analogous to our aldol addition reactions. No. And so these are, instead of starting out with an aldehyde or ketone, you start out with an ester, okay? And you get something very similar. So we can do crossed Claisen condensations, but similar to our aldol additions, you're gonna start out with a sample of just an ester and it's gonna be reacting with itself, okay? Again, we can kind of take a second to analyze what our product will be. Notice here we have 1, 2, 3. These are one of our like 1,3-dioxo compounds, and then we still have that ester group there. Okay. Yeah, so now instead of having an aldehyde or a carbonyl oxygen and or carbonyl group and an alcohol that are 3 carbons apart, we have 2 carbonyl groups that are 3 carbons apart. And the reason why we sort of want to do this same sort of numbering thing is because if I start numbering with the ester carbonyl carbon, 1, 2, 3, we can easily identify the bond that was just formed here. Okay. Reaction mechanism, basically going to be the same. So conditions are the same. We're going to do these under basic conditions. And the first step is going to be deprotonation of that alpha carbon, right? So removing that alpha hydrogen. Here, it's important that the base is chosen to be an alkoxide ion that has the same identity as your ester. Okay. Otherwise, you're going to get swapping of ester groups going on. Basically, there's going to be some side reactions. So this is one consideration that you have to make. Your choice of base is really important. It's going to be an alkoxide ion that's the same identity of whatever that other half of your ester is. And now, now we're going to have our enolate ion reacting as the nucleophile and reacting with another ester molecule that's our electrophile. So that attacks that carbonyl carbon, kicks that pair of electrons up. That gives us a tetrahedral intermediate. What do we always ask ourselves when we get to the tetrahedral intermediate step? Is there a good leaving group? In this case, there is. So instead of protonating that oxygen, it's going to come down and kick off that leaving group, which will actually be our alkoxide ion again. And this gets us to our Claisen product. There is one extra step that happens because we have this 1,3-dioxo that's formed. We know that the alpha hydrogen in the middle there is quite acidic. And so that alkoxide ion will then pluck off that hydrogen. Okay. This is actually an important step in sort of ensuring that you have a lot of product that's formed, because it's the only step in the reaction that sort of greatly favors the formation of the product. You can't go back as easily because this is so much, this guy right here is so much weaker of a base than the alkoxide ion. So it helps drive the reaction forward. And then that means that you have to have this second step where you add like water or maybe a weak acid or something like that, a step that they always call acidic workup, which basically means just a last protonation step. Okay. You can't use hydroxide ions. Like I stressed before, you have to use an alkoxide base with the same identity as your ether or as your ester. So for that same kind of reason, why can't we use an normal sodium hydroxide? Well, because sodium hydroxide can act as a nucleophile, attacking that electrophilic carbonyl carbon, and then you're left with a tetrahedral intermediate where either one of these guys are just as good of leaving groups. And so this can come down and kick off that group, and then you're left with a carboxylic acid, right? Which will get deprotonated and you'll be left with a carboxylate. So basically, you can't use any old base. Your base has to be, you're going to look at the identity of your ester and choose your alkoxide ion accordingly. And this slide just illustrates what happens if you use an alkoxide ion that's different from that. So if we use a methoxide ion, but we have an ethyl whatever ester, we're going to switch out that ester group. All right, so now we just have a different ester that we're working with. So bottom line is, again, you got to use an alkoxide ion that matches your ester. We want a crossed Claisen condensation. It's going to be the same considerations as we had before. One, you can get lucky, and as long as one of your reactants doesn't have any alpha hydrogens, you're good to go, right? So this compound here doesn't have any alpha hydrogens, so that means that this is definitely going to be the nucleophile attack, et cetera, et cetera. And so you'll only have one product. The other way that we can do this, if that isn't the case, is just like before, we'll take one of our two esters, treat it with LDA, and then titrate in the other one. And that would be a guaranteed way to get just one crossed Claisen condensation product. And just like before, we can have intramolecular Claisen condensations, which for some reason are called Dieckmann cyclizations. Again, what you're going to be looking for, I actually hate this numbering on this slide, because what you're really looking for to see if you're going to have an intramolecular reaction is if there's an alpha carbon that's located 1, 2, 3, 4, 5, or 6 carbons away from the carbonyl carbon. Exact same consideration that we had for the aldol condensation or aldol addition reactions. Okay, only going to occur when that alpha carbon is located 5 or 6 carbons away from a carbonyl carbon. And then we get this intramolecular Claisen condensation product. Okay, Claisen condensations, very analogous to aldol additions. They can take place within a sample of a particular ester where it's going to react with itself. If you want to do a crossed Claisen condensation, you need to either get lucky and have one of your esters not have any alpha hydrogens, or the LDA route, where you treat one with LDA first, then titrate in the other one. And then remember that we have these intramolecular Claisen condensations, and they will occur when your alpha carbon is located 1, 2, 3, 4, 5 carbons away from the carbonyl carbon.